A printed circuit board is a circuit on a board in which the interconnecting wires are replaced by conducting copper stripes, generally of copper, which are attached or printed or etched onto the board. The base materials for making PCB is known as copper-clad board, in which a thin layer of copper is deposited on one side or both the sides of an insulating board. The insulating board is generally made of phenolic or paper or fiberglass or epoxy. These boards are also called copper laminate boards. The required circuit pattern on the copper laminate board is made by a process called etching. Etching is a process of removing portions of a metal foil, leaving behind only the required portions of a metal foil. An etched board with only the required stripes of copper necessary for component interconnection. The areas of copper with a hole at the middle for making solder connections of the component leads. These are called pads. Holes are drilled in the center of the pads for inserting the component's leads. The copper area around the hole of a pad is referred to as the annular ring. Pads can have any shape, such as square or rectangular or elliptical, and so on. Rectangular pads are generally used for input or output connection. Square pads are used in places to indicate the first pin of the integrated circuits. Printed circuit boards can be made by one of the two methods: drawing the circuit pattern outline on a graph sheet, tracing them onto copper laminate board, and etching them manually using etchants. Making artwork of the circuit using artwork tapes and pads, or using computerized methods, and using photographic method of exposing the artwork on the laminate and etching them either manually or through automated methods. The schematic is drawn on a plain paper with a rough plan of the component placements and interconnections. The dimensions of the components to be mounted on the PCB are collected. Lead bending dimensions are noted. The schematic is redrawn on a graph sheet with a proposed component placement. Copper track dimensions. This gives the solder side PCB layout. Etch resist links are chemically resistant materials used to mask the areas of copper foil on a copper laminated board. When etched using etchants, these masked areas are protected from the chemical action of the etchants. Hence, copper only in those areas not masked gets etched. Once the required portions on the copper foil side of the laminate is painted or masked and dried, the next step is to remove the copper present in the unmasked portions of the laminate. This process is known as etching. Etching is done using any one of the following chemicals: alkaline ammonia, sulfuric hydrogen peroxide, ferric chloride, cupric chloride. While preparing the etching solution, concentrated ferric chloride solution or powder is mixed with lukewarm water. After cleaning the board using water and dried, the etch-resistant ink or paint on the layout pattern is removed using solvents such as thinner or petrol. The clean board will then have bright copper stripes and pads only in the required portions representing the circuit. The next step after etching and removing and mask or paint is to drill holes of required diameter in the pad center for inserting the components, input or output, and VCC and ground connections. Extra care is to be taken while drilling holes because carelessness while drilling may peel off the pad area of the copper. A typical component side of a PCB with the components marked on it. The standard procedure of component marking is to mark either the symbol of the component along with its code number. Dust, oil, oxide layer, or protective coating on the component leads must be removed well prior to soldering. If not, the adverse effect may result in dry soldering or improper wetting. In addition, the excessive heat due to prolonged heating may peel off the copper pad pattern, making the whole PCB unfit for use. The shape to which the component leads are to be sent has two aspects. The manner in which the component is to be mounted, to reduce the stress exerted on the component by a variety of forces, depending on the type of component lead on the space available on PCB. Components can be mounted either vertically or horizontally. The order in which different types of components are to be soldered on a PCB is very important, especially in manual soldering. The suggested order is: first, connectors and fuse holder. Second, all high voltage resistors. Third, all low voltage resistors. Fourth, all capacitors in the order of heavy to light. Fifth, active device such as diodes, transistors, ICs in the order. Soldering irons are available in different wattage ratings starting from 10 watts to several hundred watts. The wattage of a soldering iron specifies the amount of heat it can produce. As a thumb rule, higher the physical dimension of the workpiece, higher should be the wattage rating of the soldering iron. To ensure that the joint is heated to the required temperature ideally, the area of the tip face should be approximately equal to the area of the joint to be soldered. The tip should be long enough to allow easy access to the joint. The tip should not be too long, as this may result in the low temperature at the tip's working face. For electronic soldering applications, solder of tin and lead of 60/40 proportion is used. For electrical purpose, resin core solders are used. For ease of application, the flux used in addition to the cored flux in solder should be in paste form. The soldering bit tip should be cleaned, heated and tinned before starting the soldering work. Before joining two pieces of metal by soldering, the joining surfaces should be cleaned to remove foreign matters over the surface. Do not apply too much flux on a joint in one place. Apply a small amount of flux around the joint. Place the iron tip at the joint such that the tip gets maximum contact with parts to be jointed. Slowly feed the solder into the joint, starting close to the soldering tip and moving towards the edge of the joint. Continue applying the solder to the joint until complete wetting of the joint has been achieved and the joint has a concave fillet. After enough solder has been applied and solder removed, keep the soldering iron tip on the joint for a moment to ensure that all the flux on the joint has reached the soldering temperature. This will allow majority of the acids within the joint to break down, which otherwise will corrode the joint after a period of time. Generally, the time taken to make a good soldered joint is between 3 to 7 seconds from applying the soldering iron to and removing the soldering iron. Allow the joint to cool without assistance. Do not blow air from your mouth or from any other source to cool the joint. Forced cooling cools the joint much earlier than it has to, resulting in a dry and brittle solder joint, which will lead to mechanical and electrical defects of the joint. Do not move any part of the joint while it is cooling. This disturbs the chemical bonding taking place. Movement of the joint while it is cooling results in a dry joint. When a solder joint is made, the amount of flux applied should be just sufficient to make a good joint. But, quite often, there will be brown waxy substances left on the joint. This is nothing but the flux residue. In its original state, this residue is corrosive. Hence, the flux residue or excess flux must be removed from the joint before soldering can be considered as complete. Removal of flux residue requires the use of solvents. The type of solvent depends on the flux used. The surface of a correctly soldered joint will be glossy, silvery, and uniform in color. The surface texture of a correctly soldered joint will be smooth, even, and non-grainy. There shall be no signs of pitting on the surfaces of the solder. Temperature defects are caused by excessive or insufficient heating of the joint during the soldering process. It is better to practice bending, trimming, and soldering various types resistors